Hello and welcome to Naptime Videos. My name is Aviva and today you will be learning about an action potential in a neuron. Alright, let's get started. An action potential is an electrical signal that allows neurons to communicate with one another. Recall that action potentials are generated in the axon of a neuron at the spike initiation zone. Here we depict a diagram of a typical action potential. The y-axis is the membrane potential of a neuron measured in millivolts, and the x-axis is time measured in milliseconds. As you see, the diagram is broken into 4 stages for easier understanding. The first stage is resting membrane potential. The second stage is rising phase, also known as depolarization. The third stage is the falling phase, also known as hyperpolarization. And the last stage is the undershoot, also known as the refractory period. We have 5 major players that you need to know to understand action potentials: the leak sodium channel, the leak potassium channel, the sodium-potassium pump, the voltage-gated sodium channel, and finally the voltage-gated potassium channel. The first stage is the resting membrane potential. At this stage, the membrane potential will be approximately negative 65 millivolts for a typical neuron. This number is established due to diffusive and electrochemical properties of sodium and potassium. Here is a closer look at the membrane at rest. As you can see, there is a high concentration of sodium outside the cell and a high concentration of potassium inside the cell. Based off of the diffusive and electrochemical properties previously mentioned, sodium wants to go inside the cell and potassium wants to go outside the cell. During this time, the sodium leak channel and potassium leak channel, which are proteins embedded in the membrane, are open, allowing sodium to diffuse inside and potassium to diffuse outside. In addition to these 2 channels, we also have a sodium-potassium pump, another integral membrane protein, which pumps sodium back outside against its gradient and potassium back inside also against its gradient. At this time, the voltage-gated sodium channel and the voltage-gated potassium channel are closed. Please note that both leak channels will be constantly open and the sodium-potassium pump will be working throughout the action potential. The next stage is called the rising phase. Various stimuli can cause the neuronal membrane to depolarize, which means the membrane potential becomes more positive. Once the membrane potential hits negative 40 millivolts, also known as threshold, an action potential is generated. If the neuronal membrane doesn't hit threshold, an action potential cannot be generated. This is known as the all or nothing principle. The neuron either fires or it does not. Going back to our zoomed in membrane, you can see that at negative 40 millivolts, the voltage-gated sodium channel is open. Because they open, there is an influx of sodium ions into the cell, and this results in rapid depolarization of the membrane. This is why this stage can also be referred to as depolarization. The membrane depolarizes until the membrane potential reaches approximately 40 millivolts. At 40 millivolts, the voltage-gated sodium channels become inactivated and the channels become blocked, therefore stopping the influx of sodium. And the membrane potential therefore stops depolarizing. This leads us into the falling phase of the action potential. At 40 millivolts, voltage-gated potassium channels open, and there is a rapid efflux of potassium ions out of the cell. This results in rapid hyperpolarization. Hyperpolarization just means that the neuronal membrane is becoming more negative. This is why this stage can also be referred to as hyperpolarization. Remember that leak potassium channels are still open and aid in the efflux of potassium, furthering the hyperpolarization. Again, looking at our zoomed-in membrane, you can see that the voltage-gated potassium channel is now open and potassium is leaving the cell rapidly. Also, the voltage-gated sodium channel is still open, but it is inactivated, so sodium can no longer go inside the cell. The final stage is called the undershoot or the refractory period. This is when the membrane hyperpolarizes from negative 65 millivolts to negative 70 millivolts and then corrects itself back to resting membrane potential. The rapid efflux of potassium out of the voltage-gated potassium channel continues until negative 70 millivolts, when the channel closes, stopping hyperpolarization. Recall that the sodium-potassium pump is still working throughout the entire action potential, and that the leak channels for sodium and potassium are continuously allowing sodium and potassium ions to diffuse in and out of the cell, respectively. Now that the voltage-gated sodium and voltage-gated potassium channels are closed, the sodium-potassium pump helps to bring the membrane back to its resting membrane potential of negative 65 millivolts by pumping sodium ions back out of the cell and potassium ions back into the cell. After the neuron is back at its resting membrane potential, another action potential can be generated, and the whole process is repeated. And that is an action potential.